Hi everyone, and welcome to part 2 of integration by parts. At the end of part 1 we had just finished example 3, and this video will just focus on our final example, number 4. But before we do that, a quick summary of what we've done so far before we go on to that. So keep in mind, integration by parts is a way for us to take the antiderivative of something with a product of two functions, essentially. And typically those two functions will be two different things, usually a combination of logs, inverse trig, polynomial, exponential, and trig. And that's why we use Lipit to help us choose what our u should be. Example 1 was what I would call more of a very straightforward integration by parts. Very traditional in the sense you find your right term for it to be u, and then you go through the integration, and it's pretty straightforward. In example 2, I showed you how we could use logarithms. I'm going to take that back, that you can integrate logarithmic functions using integration by parts, and we did one example there. For our third example is a situation where we had to unfortunately do integration by parts twice in order to simplify the integral enough for me to be able to wrap the problem up. And that's where we left off. And so example number 4 is what I previewed in the last video as what I call the worst case scenario. And here's why. When you look at the term Lipit, the 5 types of functions that are usually embedded in these integration by parts, the first 3, LIP, the logs, the inverse trig, and the polynomials, when you take derivatives of those, they always become simpler than they were before. However, those last 2, the exponential and the trig, they don't. Exponential functions, as you know, e to the x's derivative is just e to the x, and even 2 to the x becomes more complicated because it would be 2 to the x natural log of 2. And trig functions, we know, they go in kind of a cyclical fashion, even cosine and sine. And so in this example, we are given e to the x, an exponential function, and we are given a trig function, cosine of x. So you can see we have created the worst case scenario, the last 2 that we would want to use here. Nonetheless, we're going to try to forge ahead and do this. And so exponential would be my best choice for u using the concept of Lipit. So we're going to say u is equal to e to the x, and then my dv will be equal to cosine of x dx. And just as we've done for all these examples in this video, we'll take the derivative of u, we'll take the integral of v. Now be careful with this, whose derivative is cosine, and the derivative of sine's derivative is cosine. So that's the reason why it would be sine of x. So here we go, uv minus the integral of v du. And comes as no surprise, as I would hope you would think, that I'm calling this the worst case scenario. Well, obviously the integral did not simplify enough, and so we are going to have to do a second integration by parts in order for me to do anything further here. And so with that, I'm going to go ahead, just like in example 3, highlight that in blue, and I'm going to do my work over in the blue pen. We're still going to want our u to be e to the x. Our dv this time should be sine of x dx instead. And doing our derivatives, we get that. And then whose derivative is sine? This would be negative cosine of x. And so let's set up our integration by parts and see where we get to. E to the x, sine of x, minus, and we'll switch over to blue, uv, I'm going to throw the negative sign right there instead, minus the integral of v du. So negative cosine x, so integral of v du would be e to the x dx. Okay, I'm going to do a little cleaning up to this, and then I want us to have a conversation about what's going on here. So we have e to the x sine x. I'm going to distribute that negative sign, so that's going to become a plus e to the x cosine x. Now, let me do something back up here real quick. That negative cosine, I'm going to move that negative out front. I lost the c and the o, whoops. So now when I distribute the negative sign, it will go back to being negative cosine x e to the x dx. Okay, I'm going to stop here because if we were to say, oh, well, cosine e to the x can't be integrated, so we're going to do a third integration by parts, I would stop you and say, just wait a minute. Where have we seen cosine x e to the x in this problem? Oh, right. That was the original integral that we started with. So what did we just do here? We did all of this work, and what we've actually done is we've created a more complicated problem than what we started with. Not a good sign unless we use the transitive property to help us out. Keep in mind that this integral right here in the beginning, e to the x cosine x, is equal to this, which is then equal to this, which is then equal to this last step that we have. So one thing I can do with this is I'm going to conveniently go ahead and say that this is indeed equal to the original problem, which is cosine x e to the x dx. Why would that be helpful here? Well, an integral is nothing more than just some sort of mathematical expression. And as we know, when we set up an equation, we can always move things around to try to manipulate them the way that we need to solve a problem. I see a minus integral of this, and I see the integral of this. One thing I might like to do here is I'm going to add this integral to both sides of the equation. Now, the reason why this is going to be so helpful is that it's going to create the left side of this equation, so that goes away. The left side of this equation has no integration in it anymore. E to the x sine x plus e to the x cosine x equals, and when you add two like expressions together, even if they're integrals, that's going to always be repeated addition, so it's going to be 2 times cosine x e to the x dx. And we have one final step to go, because again, my goal in this whole problem was to figure out what the integral of e to the x cosine of x dx, what is it equal to? Well, guess what? If I divide both sides by 2, I will have answered that exact question. And so the integral here is going to be equal to e to the x sine x plus e to the x cosine x, all divided by 2. Now, you could write it as times 1/2 to the quantity if you wanted to, but I'm just going to leave it this way. Cosine x, e to the x dx. The only thing that we may want to do here, keeping in mind that this is going to be, could have a plus c in it, so we do want to make sure we add that in. Now, because I don't want to erase everything, I'm going to actually put the c in front this time and put that over there. But this is going to be our final answer. And that will conclude integration by parts. So go back. Please feel free to watch any of these videos over again. And if you have any questions, please feel free to reach out to me through email or any other means necessary. Thanks again for watching.